Yeah. So hello everybody. So I'm gonna follow up on functional presentation by talking about technique of deriving work representation by using the technique sparse coding and actually variant of hierarchical sparse coding. So let me first introduce you to the problem of sparse coding. So in linear algebra, sparse coding just means that given a matrix of X. So the goal here is that you find matrix DNA such that every column of these is a basic vector. So a basic vector just basically means that the L2 length, the L2 now has a value of 1 or less than 1. And A is the sparse coding, which means that each column is sparse, so some dimension of it is 0. So the idea of sparse coding is that we try to zero out the noises in the input vector matrix X, as well as we try to give some meaning to some of the dimension of every column of A, and also data compression. So we do that by we try to minimize this loss function. This term here is specific to this paper, so let's just leave it aside for now. But when they talk about sparse coding, they usually mean this term. They usually be a regularization term here, but in this case, this regularization term is specific to this paper, and this is what the novelty of this author approach. So let's talk about the regularization term here. So we know that in machine learning, people usually introduce the regularization term just so that the absolute value of every entry in a way is remain as small as possible, to understand that it doesn't sacrifice the loss function very much, the actual value of the loss function very much. And so here the author proposes regularization term here. So it just means that for example, right, let's say that every column of A has a dimension of 26, and the author decided to encode a structural constraint on the 26 dimension, such as the 2, 3 presented here. So that just means that if for example, if dimension 0, the dimension 1 take on the value of 0, or the dimension that is defined as its descendant will also take on the value of 0. So the author decided to employ this constraint, so that just imagine that this first dimension here represents some general notion like it's like a tree, and then here you have like a fruit tree, and then you have here you have mango and like some kind of fruit here. So if suppose that this dimension take on the value of 0 here, then this all these dimension must also take on value of 0, because the general term here is being zeroed out. So any dimension that shares some similar context with must also be constrained to 0. So that is the regularization term that the author is trying to suggest here, trying to propose here. So let's talk about the input of this problem, that the input of the model that the author is trying to get the learning representation from. So the input X that I just mentioned briefly earlier, would be would have the size of C by V, where C is the number of contexts that is possible to each word. Usually, C and V is very similar to each other. So you can see that V is the size of the vocabularies, and so for every collection of corpus of word, for each word there will be an amount of V minus 1 possible word of neighboring to it, every pair of it. So so here they just calculate the points-wise mutual information value between the word. And here you can see that how this value is being calculated. We just count the occurrence of each word of a specific word in the corpus, and then count the number of co-occurrence which is neighboring, and then from there you can derive this value. So, as I mentioned earlier, we try to minimize this cost function, but since that the size of this is often very large, and computing resources is very limited, so the author decided that he would carry out an approximation of the learning process that presented earlier. So, for example, the author decided that he would pick entry in the matrix S proportionally to its absolute value, and then from the X he would derive the number, the row and the corresponding row and column in the matrix D and matrix A, and then he would carry out this calculate this loss function, and then from this loss function we calculate the derivative from this loss function, and then we update the row of A respectively. It means that we fix D and then we update A, and then we fix A and then we update D. So this is the learning algorithm that the author proposed, as I mentioned earlier. So right here you can see the term here, this the M, which is the M column of D. So the author tried to impose that every column of this will be a basic vector by directly proposing this term into the loss function, rather than trying to impose it the other way around. And you can see. So let's now talk about the experiment. So the author decided to run his model again several baseline, and put in the password. For his dataset, he used a dataset that has a vocabulary of roughly about 180,000 words. So the input matrix will have the size of roughly this number square. And here is the result of his model against several baseline. So you can see here on this table, the last two columns are his approach. Okay, the second last column is his approach, which tells the regularization, the hierarchical regularization term, and the first approach is the Sparse coding with the hierarchical regularization term. And basically, from this result, he reached the conclusion that by imposing a hierarchical structure to the Sparse coding, the model can produce better result. Just just by the regulation, the tree structure regulation term here. And you can see here that the his approach combined, the sparse coding combined with the regulation can produce result that is competitive to most of the previously state-of-the-art, which is clove. And also from here we can see that his approach can outperform state-of-the-art in three tasks, but there is two tasks that it severely underperformed to clove, which is the syntactic analogy and semantic analogies. So from that, the author decided that he would try to run the result on a bigger corpus, and since he's running on a bigger corpus, he's decided that he would only take the baseline that can scale to bigger corpus that he can run, and clove is one of them, as well as scriptgram and Stable. And yeah, you can see that this is competitive to clove. And the result down here is just that he would take the published pre-trained work embedding by the baseline, and then try to compare with his result. Right here, he just the number of dimension in the work representation. And the reason that he also try to reason that since he tried to learn an approximation, so his method should train reasonably faster than the other baseline. But I mean that looking from at smaller corpus is longer than the other approach, but when the corpus scale to a bigger size, you can see that his approach the learn time for his approach start to compare reasonably well to the other approaches. And here is some represent visualization of the work embedding that his model have learned. So you can see that the work that have some kind of similar contexts that are quite similar to each other. So as the work animal and animals here, they're quite similar to each other. As well as when he tried to grab the work in a certain vector space, you can see that the work that have similar meaning try to cluster to others, where versus work that have the opposite meaning. And that's the end of it. Thank you for your listening.